Hi everyone, and welcome back to CS103, Machines, Languages and Computation. In this lecture, I'm going to introduce you to the last of the three proof methods that I'd like you to know about, and that's called proof by induction. As you know, some sets are infinite. They go on forever and ever, and they never come to an end. If you try to enumerate the elements, you will never complete that process. So sets can have an infinite number of elements. And the most important set from the point of view of computer scientists is the set of the natural numbers, n. As you may know, we sometimes use n0 starting at 0 and n1 starting at 1. So n1 is the numbers 1, 2, 3, 4, 5. n0 is the same set but with 0 in there. Computer scientists often prefer to use n0 because of the bit pattern of consisting of all zeros being the smallest number that you can represent with bits. Now, this set, it's infinite, but it's extremely well behaved. One of the things that we can rely on with this set is that every element has a natural successor. So if I'm looking at element A, I know the next element is A with 1 added to it. Now you might think, well, that's obvious, but that's not true of all infinite sets. Some of them don't have this property, this natural successor. So if I'm looking at 2 in n0, I know the next one is 3 and then the next one is 4. And there's a natural successor relationship all the way along in the set. So this set is certainly infinite because for any element, there's always a next one, and there's always a next one, and there's always a next one, and there's always a next one. But because it has this property of having this successor relationship, it's described as being countably infinite. And that means it's one of the smallest sort, in fact, it is the smallest sort of infinity that there is. And we talk about the cardinality rather than the size of an infinite set. So a countably infinite set, like the natural numbers, is the smallest sort of infinity that there is. And we'll see some infinite sets which have a larger cardinality later on. But for the moment, all you need to know is this is a very well behaved infinite set. How can we deal with infinite sets in our proofs? If we need to prove something for an infinite collection of cases, how can we do it? Well, the first strategy is the one you've already used in your direct proofs. You use letters instead of numbers. You don't use specific numbers. You use a letter and say, let k be any integer, or let p be any member of the natural numbers, something like that. If you're using letters, not being specific, and your argument works, then you know it will work for any member of your infinite set. Another way of doing it is to use this method called proof by induction, and this only works for the natural numbers, and it relies on two crucial properties of that set. First of all, the set that you're doing this on has to have a first element, a smallest element, a start element in other words. Also, this successor relationship has to hold. In other words, if A is an element of this set, so is A with 1 added to it. So what we're going to do is we're going to form a chain reaction. We're going to prove it for the first element. We're going to then show that if it's assuming it's true for this element, we can prove it's true for this element, and that'll get the chain reaction going, and we'll see how that works. So proof by induction is used to prove statements of the form for all n which are members of, that's that funny symbol there, all n which are members of the natural numbers, some property holds of n. And what we do is, first of all, we prove it true for the first case. That's easy enough. Usually the first case is something like 0 or 1, or it's a small number anyway. We find the smallest possible value of n for which our formula makes sense. So you have to think about what the value of n is. The smallest value of n, and we see if the formula holds. If it doesn't hold, then we're done. There is no proof that formula is false. But if it's true, then we're on our way. We've proven one case. What we now do is that we assume that the formula is true just for some arbitrary case somewhere along the line, one of the natural numbers, but we're not saying which one. And we're going to assume that it's true for that. The inductive step then consists of proving that the formula must be true under that assumption for the next one. So how does that make it true for all of them? Well, we get this thing called a chain reaction. In other words, one is true. We know that it's true for the first case. And we've shown that essentially that the first case implies the second case. That's what the inductive step tells us. It tells us that for any k, the next one is true. So in other words, because 1 is true, 2 is true, because of this inductive rule here. So now we've got two cases. 1 and 2 are both true. But because we know that 2 is true, the inductive case works again. 2 implies 3. And 3 implies 4, and 4 implies 5, and 5 implies 6, and so on and so on and so on and so on. And then the whole lot's done through the chain reaction. So in the next video, I'm going to give you an example of how this chain reaction works using an analogy based on, well, curry in fact. And then I'm going to do an example of proof by induction for you. And then finally, there's an exercise for you to have a go at where you'll prove a similar statement using proof by induction.